Okay, in this video I'm going to be going over section 5.3, which is all about the fundamental theorem of calculus. So first off, let's recap what we talked about in lecture the other day, which was the fundamental theorem of calculus. So it came in two parts. So the first part, it's kind of simple, but it's about this thing called the area function. So this essentially says, let a of x be an area function, which is this weird integral, right? Where the upper bound on this integral is actually the input of the function. So a of x, the independent variable is in the upper part here. So this is what is denoted as an area function when the input is right there. And so a of x will output the areas right under the curve f of t for different values of x. So if we have that definition of this function, then it turns out that a of x is an antiderivative of little f of x. So in other words, if I do the derivative of a of x, I get back the function, which is the integrand f of x. Okay, so we'll do one quick example of that type of thing, but the more important part of this theorem is the fundamental theorem of calculus part 2, which allows me to essentially evaluate definite integrals. So I'll just cut to the chase here. If I want to evaluate the area under some function f of x from a to b, then this is exactly equal to f of x, capital F of x, evaluated from b to a, which this notation means I first put in the upper bound b and subtract off the lower bound a. So here, capital F of x, right, is any antiderivative of little f. Okay, so let me show you a couple examples using these two parts. So here's a quick one for the part 1. So let's say we have this area function, which really could be anything, right? So here it's the area from 3 to x, right, of this function, t squared plus t plus 1, dt. So how would I find a prime of x? Well, in the previous theorem, it says that a prime of x is essentially, right, f of x, correct? So what we have here in the integrand, and again, remember, t is just a dummy variable. So this is my function f of t, right? So f of t is this function right here. And so a prime of x is simply that function, replace the x, replace the t with an x. So the derivative of this area function is simply this, and I'm done. In fact, if I wanted to evaluate, say, a prime of 2, then that would just be f of 2. And so I would just plug that in, which would be 7, right? So this, right, nothing really changes. This thing becomes the derivative of capital A. So let's actually use the fundamental theorem of calculus part 2, which is the more important, I would say, part of the theorem. So here, if I want to evaluate this area, right, this is a parabola, and I want to find the area under this curve or bounded by this curve in the x-axis between 0 and 2. So we would first look at the indefinite integral of this thing, right? So remember back a couple sections ago, we were doing antiderivatives of this. So what's the antiderivative of 3x squared? Well, we know that 3x squared is the derivative of x cubed, so the antiderivative would be x cubed. And the antiderivative of 2x is x squared, right? So this, in the fundamental theorem of calculus part 2, right, this is capital F of x, right? So I know that I have to add plus c here, but the theorem says any antiderivative. So we'll just use the one that that has c equaling 0. So now if I go to the definite integral, right, I can quickly compute this area by taking my antiderivative, the one with c equal to 0, and evaluating it from 2 to 0. So this means I plug in 2, and then subtract off, plug in 0. And so I get a plus 4, and then this would just be 0. And so the answer is 12. So the area, right, bounded by f of x equals 3x squared plus 2x over, or I'll just say on 0 to 2 is 12. Okay, so that was a pretty simple example, but let's do a couple trickier ones. So we can actually compute the following area as well, right? We know the antiderivative of trig functions, so I'll just go ahead and keep this. We'll just do the antiderivative in one step here. So the antiderivative of 1 would be x, and the antiderivative of negative sign would be a positive cosine. So here I'm evaluating this from 0 to pi. Plugging in pi, I would get pi plus cosine of pi minus 0 plus cosine of 0. Now be very careful here because cosine of 0 is actually it's actually 1, so it's not 0 in this case. So here I get pi. Cosine of pi is negative 1, so that would be pi minus 1, and then minus 1, because this whole thing would be equal to 1. 0 plus 1 is 1. So here my answer is pi minus 2, which is a positive number, right? Pi is about 3.14 minus 2, so this has some positive area to it. Okay, so lastly, let's try one that has an e in it, so an exponential function. So first off, let's take that 10 out, so I can just pull that 10 right through the integral, right? That was a property of integrals there. And then I have e to the 2x. So this one's a little tricky because that 2 is up there, but we can actually remember what was the derivative of something like e to the 2x, right? So when I do the derivative of this, I have to use a chain rule, so that gives me 2 e to the 2x. So I know that when I do the derivative of this thing, right, a 2 has to pop out. So if I'm going to do the antiderivative of this thing, right, I must have to divide by a 2, because when I do the derivative of the 2x, right, that'll cancel that 2 and leave me with a constant of 1, which is pretty much what's right here, right? So let's check. So what would be the derivative of 1/2 e to the 2x? Well, the 1/2 stays, and then the derivative of e to the 2x is 2 e to the 2x, which gives me e to the 2x, because the 1/2 and the 2 cancel. So that is indeed the right antiderivative. So we have 10, and then the antiderivative of e to the 2x we just found was 1/2 e to the 2x, and then I want to evaluate that from 0 to 1. So here, before I evaluate the antiderivative, I can simplify a little bit. So this would be 5 e to the 2x from 0 to 1. And now let's plug in my stuff. So this would be 5e squared minus 5e to the 0. And again, be careful here, e to the 0 is 1. So I'll be left with 5e squared minus 5, factoring out of 5. I get this. So this would be my area. All right, so that's how you use the fundamental theorem of calculus.